Did you have a good weekend? Was it hot? Today is much better, I think. Okay, so let's continue. So remember, we were talking about processing in memory. I'm going to continue that lecture, and we're going to finish it, and then we're going to talk about simulation a little bit. Hopefully, we'll start with latency, low latency memory. But I just want to remind you the required review papers. Actually, I added one more over here. So these are the ones. Who has started reviewing papers? Anybody? Okay, that's great. And you saw the examples that I sent. Hopefully, those are useful. If you have any questions, please let me know. And I sent a video also, I think, describing how to review papers. So hopefully, you'll have fun reading these. This one, this one, this one, you already know. And I assigned these two based on the voting that we did last time on Friday. So everybody wanted to review these two papers. So since you wanted it, go ahead. And I think you'll have fun reading them. And I also added this one. This one we didn't talk about, but I think we should have another reading related to reliability, scalability, and I wanted to start with the original paper that we've done in the area. Even though, as I said, it proposed a mechanism that was not implementable at that time, it had a vision, and it also has a lot of interesting analysis, which hopefully you will benefit from. It also discussed Bloom filters. I think those are fundamental data structures that you would benefit from knowing, even if you are not interested in anything else in this course. I think it's good to know about Bloom filters. And I would recommend that you read the original paper by Burt and Bloom in 1970 also. Normally, I teach that to freshmen, actually, at ETH. When I talk about some of the issues in architecture, I think it's good to know about Bloom filters. And I discussed that paper very briefly. But we already discussed it on the, I guess, green board last time. Okay, so these are the required ones, and I'll assign a few more of these. But I think the best way of approaching this course is reading a lot of papers, since there's nothing else really as assignments. If you would really like to do research in related areas, I would suggest reading more papers, and I put some more over here. We're going to discuss this one very soon, actually. It's going to be the more minimalist approach to processing in memory. How can we actually do the minimal thing, and what kind of benefits do we get, and what is that minimal thing? But I would recommend this paper also because it takes a completely different approach to processing in memory than the previous papers that I assigned as required reviews. But I don't want to assign this as required because then there'll be too many processing in memory papers as required ones. I mean, this one you know already, we discussed it. This one I mentioned also, so please take a look if you're interested. This one has, this is very similar to the Ambit paper, which is already assigned, but there are some future work sections in here that you may be interested in, if you're interested in future work, future directions in DRAM processing. And also, I think the DRAM background that we've written in this paper is better than any of the other papers that we've written in the past. Of course, this is new, right? So we have all the background, so we can write things much better. So I really like the DRAM background here. It starts from very, very bottom up and goes all the way up to the chip and module. Okay, and this is the original Rowhammer paper. Now, you're reading the retrospective of it, but if you want to know what the original one looks like, I would recommend reading this one, certainly. That's 5 years ago. You're reading 5 years after. And this is, we've discussed this already, so I just picked some of these papers. And this one is also introducing some new topics. We didn't discuss this. We'll see if we have time to discuss some of these quality of service aware memory controllers. But if you want to do one reading, this is one that I would recommend. I actually recommend this one for my students when they are getting ready to write papers. I like the writing style here. Well, I'm not biased, right? Clearly. But I did put a lot of effort into this work, clearly. Of course, you can always do better. There are parts that are not perfect. But I like this style in this work for sure. Okay. Well, I don't know why this is animated. But this is another one that I assigned as optional review. I don't think we're going to cover flash memory, but if you're interested in this, this is really the state of the art in error-related issues in flash memory. And we're going to talk about this today. This is a very short paper on memory simulation. And if you want to do research, architectural research in this area, I would recommend starting with this simulator because I think the barrier to entry is very low with a simulator like this. And then we've discussed this also. That's another optional review. And I can keep adding optional reviews, as you can see. But these are my selections based on what we've discussed and what we're going to discuss very soon. And this is, I think, we discussed briefly. Hopefully, we'll have time to discuss more. I think this area is also very interesting, using memory for different security primitives, including random number generation. And I like this one because I think this can open up a lot of other interesting work. So if you have ideas, I'd be happy to chat. And if you don't want to read the paper, you can watch the video of my student also. He recorded a video describing the paper, basically, presenting the paper. Okay, of course, clearly there are too many to list, right? I could keep listing all of these. What I provide is just a sampling for you, and many other important references are in lecture slides. And there are some other references like the Google paper in ISCA 2015 that I would recommend. I think some of you may be interested in reading it. I'd recommend rigorously reading as many as possible if you have time, or if you can always create time. And recall that chance favors the prepared mind. I really believe in this. What is the benefit of reading? If you're rigorously reading, you really build knowledge in an area, and you're ready to make big contributions, I think. And that's great preparation. And also, you can use my website as a resource for papers and artifacts. We actually have a lot of artifacts, like software and hardware artifacts that you can download. Well, of course, you cannot download the hardware, but hardware code. I guess FPGAs, you'll have to get them yourself, as I mentioned in the earlier lectures. Okay, so you know where that is. So that's the end. So that's the prologue of this lecture. But this is where we left off. We were talking about computing architectures with minimal data movement. And we looked at different types of processing in memory. And I called everything processing in memory, if you remember. I set up the lecture that way. But the goal is really to minimize data movement, in my opinion. And we essentially covered all of this, minimally changing memory chips. And we were looking at exploiting 3D stacked memory. And essentially, we were in 3D stacked memory, we were looking at answering some of these questions. Basically, we looked at changing the entire system to get a lot of benefits. We talked about the Tesseract paper, which is one of the required readings. How do you actually design a 3D stacked logic and memory-based system that can do processing in the logic layer, such that you can accelerate an important application like graph processing. That was changing a lot in the system, and you got a lot of benefits in the end, about 13 to 14x, right? And I believe you can get more, but we didn't optimize the system. And then we looked at more easier forms of processing in memory, like simple function offloading. This is the Google workloads paper, and some of the other works, like accelerating linked data structures, for example, offloading pointer chasing functions to memory. Now we're going to look at, even that requires actually changes in the system, right? For example, we talked about the virtual memory challenge, right? Coherence challenge. We're going to talk more about the coherence challenge, but virtual memory address translation challenge is a big challenge if you offload functions to memory. And I don't know of any really, really good solutions to that problem, frankly. If you're interested in doing contributions in this area, solving that virtual memory challenge could be big. In general, re-examining the virtual memory mechanisms with emerging memory technologies is a really important direction, I think. Let's take a look at what is the minimal thing that you can do if you have 3D stacked logic plus memory, or some form of processing in memory. I think this is not restricted to 3D stacking, but we're going to assume 3D stacking. Basically, what if you don't want to change the system much, and you don't want to change the programming at all? Even simple function offloading requires some changes to the programming, right? Of course, you can do it transparently to the programmer, like we've discussed briefly also. If you do it transparently to the programmer, maybe not, but usually the big benefits come when the programmer actually identifies these portions of the application that needs to be shipped. But if you don't want to do that even that much, and that's the idea that's presented in this PIM-enabled instructions work, which was also published in ISCA 2015. So let's take a look at what that is. So the goal is very simple. We would like to develop mechanisms to get as much as possible out of near data processing with minimal cost, minimal change to the system, and no changes to the existing programming model. It's sequential execution, basically. That's what we want. And there are two key ideas. I'll give you the ideas very quickly. One idea is very simple. You expose each processing in memory operation as a cache-coherent, virtually addressed host processor instruction. Basically, we add new instructions called PIM-enabled instructions. They're executed in the host, and the host decides whether to ship it or not ship it to the main memory. And there's a key restriction here, and the restriction is that the instruction can operate on a single cache block. Basically, the boundary of the instruction is that cache block. And that eases a lot of issues because you just need to, it's very similar to a regular instruction. You just need to translate the address for that particular cache block, and you just need to ensure coherence for that particular cache block. Right? You don't need to deal with a huge page, for example. And that's the idea. Of course, this is going to make benefits lower as well. Then this is one example. If you want to do PIM-add, I'm going to show you an example inside the program later on. This is basically the instruction, PIM-add R1, R2. And R2 is a memory location over here. You basically take R1 and add it to the memory location, value in the memory location that has the address in R2. And then you can do it in the processor or in the memory. That's the idea. Now you have a choice, basically. So this leads to no changes in sequential execution and programming. Well, it's just an instruction. No changes to virtual memory. You don't need to deal with that because the processor translates the addresses. Minimal changes to cache coherence. You need very little change to ensure that if you ship this to memory, nobody else actually touches that cache block. That mechanism actually exists in most processors today. They can do cache block blocking. The difficult part is really doing this locking for multiple cache blocks. But we're not touching multiple cache blocks here. We're touching only one cache block. And also, there's no need for data mapping. This is another issue with processing in memory. If you want to actually ensure that you ship some function to a memory module, you need to ensure that if you want to get the benefits, all of the data that's manipulated by that function should be in that memory module, right? If you need to go to some other memory module, so if some of your operands are in some other memory module, that now you still need data movement. We're going to talk about that a little bit. But this doesn't have that issue, basically. This sidesteps that issue because you have a single cache block. That cache block is only in one memory module, right? There are no systems that I know of actually that distributes a cache block across different memory channels. That doesn't exist today. Yes? Say it again. If
we use 2 or more cache blocks.
That's right. Yes, exactly.
So do we need to change the sequential execution model?
Not the sequential execution model, but you need to ensure that you don't use 2 or more cache blocks, basically. So basically, if you're updating a value in memory, for example, adding, then this works without any problem. But if you have a more sophisticated instruction that you want to add, you need to ensure that you're not operating on 2 or more cache blocks. Basically, if for some reason your instruction, the compiler can cache that, for example, if somehow you're operating on 2 cache blocks. If it doesn't cache that, the hardware needs to catch that. And it shouldn't execute the instruction if it's operating on 2 cache blocks in this model. But the programmer should not deal with that, basically. OK. And the second idea, which is orthogonal, completely orthogonal to the first idea, is to dynamically decide where to execute a PIM-enabled instruction. Basically, there are 2 places to execute this instruction, either the host processor or the processing in memory engine. And we have a mechanism based on simple locality characteristics and simple hardware predictors, which I'm not going to go into detail about. But basically, the key idea is if the data that you're operating on, if the cache block is in memory and not in the cache, execute in memory. Otherwise, execute in the cache, meaning the processor. You can, of course, extend this model. If you have different processing units across different parts of the hierarchy, you can decide where to execute this particular instruction, right? If the data happens to be in the L3 cache, and if you have a PIM-enabled instruction execution unit in the L3 cache, maybe you ship that instruction to that unit. OK, so these are, I think, powerful ideas that could be generalized. The overall principle is to execute each operation at the location that provides the best performance and minimal data movement. Let me give you an example. This is the PageRank example that we looked at in Tesseract, for example. Basically here, we're adding some value to the rank, and we're looking at all of the successors. So in a conventional system, basically you need to bring in the entire cache block into the host processor, and then you need to write back the cache block back into main memory after you do the update. So essentially, you're transferring 64 bytes in and 64 bytes out, assuming that's the size of your cache block. Right? Now we're going to replace this with this PIM-add instruction that has the address of this memory location and that you input the value also. In this case, and that's translated to this ISA instruction. And then basically you send the value to memory if the data is in memory, if it's not in the cache. You just need to send 8 bytes essentially, right? Assuming value is 8 bytes. So off the bat, you save about, you reduce the bandwidth requirement by 16x. Right? That's the idea. Okay, the question is, of course, when do you do it? I guess there are many questions here, right? What are the instructions, first of all? What instructions do you add to the ISA? Now that we didn't completely answer, but I'm going to show you examples of instructions. This is one example instruction. In my opinion, the best way, as I said last time, is you have a configurable logic layer, and then you can potentially even generate these instructions dynamically if you have a dynamic compiler. But you will see that some of the instructions will be even more complicated than this to get benefits out of your applications. Okay, so the next question is basically, should you always execute in the memory? Should you always execute in memory? And we did that study based on the instructions that we selected, and these are graph processing workloads again. We decided to offload all of the instructions, all of the PIM-enabled instructions to memory. And some applications gained a lot of performance, but some applications lost a lot of performance. So this shows that it's not always a good idea to ship even an instruction to memory, because you may have very good locality in the caches. That's the idea. So here, because you're shipping things to memory, you're reducing the memory bandwidth. But here, caching is very effective. You're actually increasing the memory bandwidth consumption by actually sending the instructions to memory. So you don't want to do that always. That's why we wanted to develop an adaptive mechanism. Okay, so this is another example. So what are the instructions? Let's take a look at the instructions. So we also have the p-fence instruction. This is very similar to what we had in the tesseract, the barrier, right? You keep sending these instructions to memory, but when do you get acknowledgements, right? When do you actually say, okay, I'm going to stop and wait if all of them are complete? That's part of the program. This is very similar to the fence instructions that we have in systems today that ensure that all of the memory operations complete before you can execute any code after that. That's the idea. Okay, so these are some instructions. It's very interesting. And these are the instructions that we came up with, of course, based on our experience with the programs. But you can see that there's a floating point add over here, and different applications exercise different instructions. A lot of them are graph processing algorithms. Some of them are in-memory data analytics. Some of them are machine learning, like the support vector machine. Dot product is a good instruction over there. So it's a sum definition, of course, which is not here, but its input is 32 bytes, output is 8 bytes in this case. There's an instruction that computes Euclidean distance for the stream cluster application. So if you're actually doing streaming analytics, you have a lot of data coming and you're comparing the data similarity. Euclidean distance is one metric that this workload uses to assess data similarity. And it turns out that's a good instruction to execute in memory. And you can see that its input is 64 bytes, output is 4 bytes. Some hash table probing mechanism, if you have hash join, which is used by databases, that's another good instruction to add. And there are other, like minimum, 8-byte integer minimum. You find the minimum value, minimum byte in 8 bytes. These are the instructions that we came up with based on the workloads that we studied. I believe there will be more instructions clearly. And this is more of an art, like how do you figure out all of the interesting instructions. And as I said, maybe there should be a better interface that enables expression of these instructions for memory. I think that remains to be seen. In this case, we assume that the ISA has these instructions clearly. But last time we talked about expressive memory, right? I mentioned that we have this paper that's called expressive memory that changes the interface between the hardware and the software. And I think looking at more expressive ways of expressing computation to be done in memory is very important going into the future. Maybe we should have less rigid interfaces between the hardware and the software. Okay, so I think I already said this. I'm going to skip all of these. I guess basically the execution is atomic between different PI. So you need to have an execution model, but all of these are actually existent in existing systems. And the execution is not atomic with normal instructions, so you use p-fence for ordering. That's also very similar to the m-fences that we have in existing systems. the key here is the reason this works well is you have a single cache block restriction. Each PEI can access at most one last level cache block. Actually, similar restrictions exist in atomic instructions today in ISAs because the atomicity support that's provided in existing ISAs is limited to single cache block because there's no easy way of ensuring atomic updates to multiple cache blocks today, except for systems that provide transactional memory. Do you know about transactional memory? Okay, some people do. Basically, the idea is very simple. So you know about locking. So you have a critical section. You acquire a lock, and then you execute the critical section, and you release the lock. Right? That is supposed to execute in isolation, and no one else is supposed to get into that critical section at that time. Transactional memory does this automatically, completely, basically. As opposed to locking, the programmer says, I want this piece of code to be executed as a transaction such that it's completely isolated. Nobody else can execute that piece of code or touch any data that I'm going to update in this piece of code. So the programmer says begin transaction and then end transaction. Any code that's in between, that is executed in isolation from other. Basically, no other code will touch the data that this code will update or read. Of course, read to read is all. If some other code reads the same data that this code is reading, that's fine. It's not a conflict. Basically, you're not supposed to conflict with this code that's transactional. So some processors support transactional memory that it allows multi-cache line updates, but the hardware for that is actually relatively complex. And if we talk about transactional memory, this is going to be a very long lecture. But if you're interested in the idea, the first paper that developed it was in ISCA 1993 by Maurice Hurley and Elliot Moss. And it's a very seminal paper. I would say if you search for transactional memory, Hurley and Moss, you'll find it. And then recently, processors started implementing limited forms of it. Okay, if you have transactional memory, you can have multi-cache line updates, but most systems actually try to avoid that because it's expensive. So we actually want to have a single cache block update that's much more practical and easier to implement. Actually, transactional memory is interesting because it could enable processing in memory a little bit also, because you can say transaction begin, and that could be a PIM-enabled transaction, right? You could actually extend the concept that I just said, PIM-enabled instruction, to PIM-enabled transactions. Anyway, I'm getting ahead of myself maybe. Brainstorming right now. Okay, so what are the benefits? Basically, each PIM-enabled instruction is bounded to single memory module, so you don't have the data mapping problem. It's easier to support cache coherence and virtual memory, as I said, because the instruction is translated by the processor, and the memory side doesn't need to do any translation, any access control. All of them are done in the processor before the instruction is shipped to memory. And of course, you can also do simplified locality monitoring because you're looking at only a single cache block, and the decision is that, is this cache block in the cache or not? Meaning that if it's in the cache, I'm going to execute it in the processor. If it's not, I'm going to ship it to memory. Okay, so this is an example PIM-enabled instruction microarchitecture. I'll go through this relatively quickly, and this is also cartoonish. This is just an example. Essentially, you need to have mechanisms to execute PIM-enabled instructions in the host processor. This doesn't need to be separate. It could be part of the out-of-order core over here, but we wanted to show this as an example. And if the instructions ship to memory, you should be able to have mechanisms to execute them in the memory. In this case, we added PIM-enabled instruction computation units in the memory controllers. If you have a logic layer, this is easy to do. Right? But you could also imagine these instructions being executed inside a DRAM chip if you have that capability. Right? You just need to support the instructions. So the idea is more general. Of course, it's easier to implement if you have a logic layer. And then, of course, you need to have some management unit that basically, this is where we have the locality monitor that we check to decide whether to execute the instruction here or here. And this is also where we lock the cache block. So if the instruction is actually sent to here, you first acquire the coherence permissions, just like any other cache block in the system. Once you acquire the coherence permissions, you lock that cache line such that no one else can access this cache line that this instruction is operating on over here. And once you're done, you need to unlock it, of course, and then you need to acknowledge it. So it's actually not a lot of additions to the system. It's very different from the tesseract, right, as we've seen. Okay, so these are some initial evaluations in the paper. I'll go through these relatively quickly also. These are the workloads that we examined: large-scale graph processing, machine learning and data mining. And we actually looked at 3 input sets because input set matters a lot here, and some simulation. I guess these are the one slide summary. You get about 47% average speed up with large input data sets. It's not 13x again. It's not 2x. It's just 47%. But it's not bad, I guess. And the energy reduction is also not bad, especially if you select the instructions carefully. So let's take a look at some of these over here. So this is with large data sets. And of course, we selected the instructions carefully here for the workload. And this is the 10 workloads over here. And this is the geometric mean performance improvement compared to the baseline. Baseline is CPU only, meaning that there is no processing in memory. So PIM only, executing these instructions that we selected always in memory provides some performance, which is, I think, 45% or so. And the locality-aware mechanism basically makes the decision dynamically. Either executes the instruction in the memory or the processor, and that improves performance slightly. So it's not a perfect mechanism. In large input data sets, it's actually better to execute. Most of the time, it's better to execute in memory, but sometimes it's better to execute in the processor also, depending on whether you cache the block for some reason, right? Or maybe maybe there are other instructions that should also be shipped to memory. You could argue, but anyway, let's not go and get into that. So you can see that this reduces actually the off-chip transfer. And you can read the paper for more detail. For most applications, we reduce the off-chip data transfer, in this case, significantly. Some of them we don't reduce that much. Okay, if you look at small inputs, the story is completely different. Small inputs means the input sets actually fit in the caches, on-chip caches. So executing things, sending these instructions to memory actually reduces performance. In this case, a lot of performance. You can see that on average, performance is reduced by about 20%. And this is an outlier in this case, actually. Even though it's a small input, you get a lot of conflicts. And as a result, it's better to execute in memory. But the decision mechanism essentially gets rid of that performance loss. If you look at this locality-aware mechanism, in almost all cases, the performance loss is curbed. So the decision mechanism does the right thing and improves performance by a little over here, as you can see, on average. So that's why it's important to actually have a dynamic decision mechanism, runtime decision mechanism that decides where to execute these instructions. And I think that's a general problem with processing in memory. Even though the programmer says, okay, you should execute this particular function in memory, it's always good to have a runtime mechanism that takes that as a guidance and maybe decides, makes its own decision as to where to execute the function. Because most of the function's inputs or data could be in the caches, right? Who knows? And I think this is going to be one of the important challenges in memory, how to design runtime systems for this kind of execution. Okay, so you can see that if you ship these instructions to memory always, you lose a lot of, you increase the amount of off-chip data transfer a lot, because most of the time caches are very beneficial for these small input cases. Medium data sets are also interesting, as you would expect. If you always ship these instructions to memory, it turns out most of the time you gain performance, very little of the time you lose. But if you actually have a dynamic decision mechanism, you actually do much better. Not in all cases, but especially in these cases over here, you do much better. So dynamic decision mechanism buys you a lot better performance. Of course, this is not the perfect decision mechanism. You can read it in the paper, but you can see that we're losing performance sometimes compared to PIM-only execution. And there are multiple reasons for that, but let's not go into that. That'll be a lot of detail. And this is the energy consumption of the entire system. So in small and large, medium input cases, executing always in processor, in memory, increases your energy, which is not what you want. In large input case, it decreases your energy. But if you're locality aware, if you dynamically decide, you actually reduce energy, little here, a little more here, and a lot here, as you can see. This is about 25% over here in the large input sets. Okay. Any questions? Yes, please. Which one? This one? Okay, yeah, sure. You're still reading? I'll overlap your reading with my drinking. Sounds good? And the details are in the paper. I'm giving you the high key points over here. Okay, so let's move on if you know no questions. So let's talk about the advantages and disadvantages of this approach a little bit. So this is actually, as far as I know, this is the simplest approach to processing in memory. I don't know if anybody else can come up with a simpler approach. I don't know. But this is simpler. Of course, it requires an ISA change. Somebody needs to add instructions. Some people think that it's not simple. But I think it's not bad. We need to rethink the ISA interface a lot anyway, as we discussed with expressive memory a little bit. But it's simple because it has no changes to the programming model, and no changes to virtual memory infrastructure, very little change to coherence. But that little change infrastructure already exists. And it also dynamically decides where to execute an instruction, which is an orthogonal advantage. Of course, this has disadvantages like everything else. Every idea has advantages and disadvantages, clearly. And the biggest disadvantage, in my opinion, here is it doesn't take full advantage of the PIM potential. It gives you 40% or so, let's say. But we know that PIM potential is much larger than that, right? In graph processing, we saw at least 13x. And I think that's just the beginning of it. But maybe this is a baby step to get there slowly, right? So this is maybe a more adaptable approach. And actually, industry is very interested in this sort of approaches because they don't want to jump to something big. Of course, there's some industry that wants to jump to something big, and those are the disruptors, right? So there are different kinds of industry as well. But some industry actually is very interested in this sort of minimalist approaches so that they can adopt a new technology much more easily. Yeah, and as I said, the single cache block restriction, which enables this, is also the most limiting part of it. Because you're not able to operate on an entire row, for example. A lot of the benefits that we discussed come from operating on multiple data elements at the same time. Maybe there are other disadvantages that you can find. But I think this is the biggest disadvantage over here. And this is, that's one of the reasons I assigned this as an optional review. So if you're interested, there's a lot more in the paper that discuss the design choices, etc. And I think going forward, expanding PIM-enabled instructions to be more powerful is going to be a good research topic. If you're interested, that's a good area also. Okay, any questions? Did I go too fast again? Okay, not this one. Okay, so let's talk a little bit more about simpler PIM. Again, I'm not going to talk go a lot into detail about many of these papers, but we discussed this briefly last time. This is also another simple approach to PIM, processing in memory. As I said, this offloads functions to the memory side. But that offloading is mostly done by the programmer doesn't need to do anything, essentially, in this case. It's the compiler's job to decide what functions to offload. But it's still a function in this case, meaning that you need to have the infrastructure on the memory side to be able to execute all that function. So it could have multiple cache blocks in this case. If you have virtual memory in your GPU, you need to have the translation mechanisms also on the memory side. And it turns out this also buys you about 30 to 50%, according to our results. So our results are actually very much in line between these two papers. This is completely in CPUs, this is completely in GPUs, and you get about 30 to 50% in these simple approaches. So you don't go up to 2x. And as I said, I already discussed this also. This is another approach where you change the memory controller such that you automatically, completely transparently offload these dependent cache mistraversals to the memory controller. And our results here also show that you get about 30 to 50%. It's very interesting, I think. These are completely different infrastructures, completely different people, as you can see. And maybe the only common part over here. But essentially, you get about 30 to 50% with these very simple approaches. And this is another one. This I like a lot, actually. This is not about automatic offloading of code. Basically, you don't offload code. Here, you offload prefetching mechanisms. Essentially, Renhead was my thesis, actually, and recently Milad had also done a lot of interesting work to improve its performance. The idea over here is basically offload prefetching threads to the memory controller. You don't offload code, but you offload essentially a thread that does prefetching to the memory controller, and the memory controller keeps prefetching data into the processor. The execution is still done in the processor, but we're just offloading the prefetcher. And it turns out this also buys you about 30 to 50%. I don't know, we haven't combined all of these mechanisms, so I don't know what the combination will buy you. But 30 to 50% seems to be a good ballpark for performance improvements with these simple mechanisms for offloading. Okay, and I would recommend all of these papers, of course, but if you're interested in prefetching, I'd recommend this one. Okay, so there's also data coherence support. We're going to talk about this a little bit more, so I'm going to skip this. But cache coherence is one problem that we haven't talked a lot about. If you're offloading some code to memory and that code is touching some cache blocks, and the processor is also touching some cache blocks, how do you ensure cache coherence at the same time? And this is, as far as I know, this is the first cache coherence mechanism for processing in memory. The idea is actually, before I go into, maybe I'll talk about the idea later on. Let's defer this to the other part that we will discuss. But this is an extended version of this paper that's appearing actually next week at ISCA. And if you're going to read, if you don't want to read a lot, read this version. This is only 4 pages. If you want to read an updated version and read much more, this is a 14-page paper. The basic approach is the same. This, of course, solved some issues that this one had. And also, this has much better evaluation in terms of applications and partitioning of the data and code. Okay. So this is a big challenge, as we've discussed. I like putting these because it's good to use these as when we want to change some direction. And we're changing direction. And let's talk about how to enable adoption of processing in memory. Any questions before we move into that? Actually, we've already been talking about that a little bit when we talk about this minimal approach. If you want to get most out of processing in memory while paying minimal cost, you're already thinking about adoption, I think. But adoption is actually beyond that. Now, what does adoption mean? Adoption means that you have a paradigm shift. Clearly, processing in memory is a paradigm shift because there's no place today where we do processing other than the processor and accelerators. If you want to change things in such a big way, you need to ensure that somehow these ideas are adopted. Otherwise, it may be useless, right? And in fact, I think this adoption is really, really important because maybe I'll give you a story. How many of you know about the data flow execution model? Yes, some people. Okay, a lot of people. That's good. Do you know when it was first developed? 70s. That's a good one. More precise? That's a harder one, yeah. Say it again? 75. You're close. It's 74. ISCA 1974. That's ISCA 2 by Jack Dennis. It's a static data flow approach. That's a beautiful paper. And later, a lot of work was done at MIT. And Arvind, how many of you know the name Arvind? Okay, that's good. So Arvind is one of the early pioneers in data flow. And the idea was basically to change the instruction set architecture completely such that you could express the data flow between instructions and operations. And that enables a lot of parallelism, clearly. And that ensures that you don't need to do any of this out-of-order processing inside the hardware, right? Of course, that comes after. Out-of-order processing is earlier, but also after at the same time. There are multiple approaches to it. But basically, he gave a keynote in ISCA 2005 describing the lessons he learned out of all of that data flow research. And essentially, his message was, and I believe data flow actually has been very successful in FPGAs. For example, a lot of FPGA-based execution models have been very successful in adopting data flow, because what you're mapping is actually a data flow engine in FPGA if you want to get a lot of performance out of it. But data flow has not been extremely successful at the ISA level. And he said that we should really have focused on adoption. We did a lot of work in hardware enabling this, but we should really have focused a lot in software also and figured out a way of actually bridging the gap between software and hardware. And I actually understand that. I believe that also because it's very hard to change the world because the world writes a lot of software. And if your execution model is completely different and you don't provide a way of bridging the gap between how the software is currently written and your execution model, then basically someone needs to provide that gap if somebody is going to adopt data flow execution. And if that gap is not bridged, then the ideas will not be adopted. Now, data flow, I think, has been very successful, don't get me wrong. It's been an extremely successful paradigm, but not in the general purpose domain yet. In the general purpose domain, we still have sequential ISAs, right? There's no data flow. The instructions are completely sequential, and we still have a program counter. In data flow, there is no program counter. Everything basically operates in pure data flow, at least. There is no program counter. So, okay, that's why adoption is very important. You may have a very powerful idea, but that may not be successful. So what are the key challenges in terms of that basically affect the adoption of processing in memory? Let's talk about that a little bit. This is in one slide, and you're already reading a paper that talks about some of these challenges. I think one of the big challenges, again, software, right? What is the functionality? What are the applications for processing in memory? What are the workloads that would benefit? Understanding the space is really important, and providing a path for those applications to take advantage of processing in memory is really important. I think there's a lot of work to be done in this area. Like, what are the common functions that should be in processing in memory? This is more of a top-down approach. Earlier, we saw kind of a bottom-up approach, right? We said, okay, DRAM is very good at doing these and or not, and copy. That's a very bottom-up approach. We didn't, even though I said I motivated with the application a little bit, it was really bottom-up. We just said DRAM is very good at it. Now there are a bunch of applications that can take advantage of it. That's good, but we should also do the top-down approach, I think, understand like what are the application characteristics that are amenable to processing in memory. What are the functions? What are the smaller instructions? So understanding the space is really important. So that's very workloads, essentially. The second is clearly ease of programming. And we've been discussing this in various forms. If you want to change everything to program PIM architectures, that may not be easy, right? Basically, we need to create some interfaces to ease the programming. We need to provide guidelines to programmers to decide what should be offloaded, what should not be offloaded. And that, I think, ties nicely with this one. And also, I think we need to provide a lot of compiler and hardware support. Because if the compiler actually enables and lifts a lot of the burden from the programmer, maybe that's a good thing, right? The downside is, of course, as we've discussed, these programmer-transparent approaches, for some reason, don't give you a lot of performance, according to our experience and other experience in the field. But maybe that's one step. You enable these compiler approaches, and then they become better over time, right? Okay, I'm just philosophizing right now. But these are important, and these are all research topics, I think, as you've been reading in your paper, hopefully. The third one is system support. We've discussed virtual memory before. I'm going to discuss a little bit more coherence. Once people start executing code, you need to ensure virtual memory is somehow satisfied, and you need to ensure you don't break coherence clearly, right? And this is especially important when you're partitioning the application between CPU and processing in memory. There are a lot of coherence issues if both of them are working on some part of shared data. We've discussed this briefly, but we need runtime systems for deciding whether you should schedule the code in the memory or in the processor. Runtime systems that help the data mapping problem, because if you punt the data mapping problem on the programmer, essentially you're increasing the cost of programming. Basically, that's an adoption barrier. But if you have a runtime system that automatically maps the data or automatically figures out the data mapping, okay, all of your data is here, so I'm not going to execute this code in processing in memory, or somehow I'm going to gather the data dynamically into this place, and then I'm going to ship the function there. The programmer doesn't need to do much in that case, right? So that's also important. And also figuring out how to do the access sharing control between different processes. And also while you're executing code in memory, there could be other cores that are accessing memory, right? How do you actually deal with that conflict, deal with that interference? This is another type of quality of service problem that will be there. So providing runtime systems that can handle that is going to be important. Clearly, these words have a lot of research topics that they're touching over. And on top of this, I think we need infrastructures, good infrastructures, to assess the benefits and feasibility, because we don't have these systems yet, right? And we need to build infrastructure to somehow understand the workload characteristics, somehow simulate the benefits that you would get, essentially assess the benefits and feasibility of these processing in memory mechanisms. And I think this is really, really important also, because if we have the wrong infrastructures, we may get wrong data, right? That's why we've been focusing a lot on the infrastructure aspect also. We've been looking at a lot of these aspects clearly, but there's more. There's a lot of room to look at more. Essentially, we need to rethink the entire stack, I think, as I put over here. I didn't even talk about devices over here, I think, because there are also hardware-related adoption issues which we've touched over so far that are not really fully reflected over here, right? There's also, like, cost is one problem in hardware. But I think those can be overcome with some changes. And again, I think we can get there step by step. So PIM-enabled instructions was developed for that reason. What is the minimal step that you can take to get you closer to a more data-centric execution paradigm? Okay. Is it too hot still in the back? Oh, is it too cold now? Well, that's a good problem to have, probably. It's easier to solve.
Okay for you?
No, it's okay for me, yeah. It's getting colder, yes. Okay, so let's take a look at a couple of these challenges in a bit more detail. Again, I'm not going to go into a lot of detail because we want to move on to other topics also. But one of the challenges is code mapping. Essentially, which operation should be executed in memory versus in the CPU. And this is something we tackled in the GPU context also that I didn't fully talk about. And you can read the paper. And that's clearly an important problem. The second is data mapping. How should data be mapped to different 3D memory stacks? So these are different controllers and different stacks. And if you want to execute an operation here, you'd better have all of the data that's required by that operation and all of the functions, or that function over here, right? If you're adding A to B and storing the result into C, and if all of them are in different modules, then it's better to do that operation in the processor, probably, right? I don't know if it's better, but you don't gain much by shipping it to memory because you need a lot of communication. So somehow you need to map your data nicely. And I think this is one of the annoying problems as we've discussed the data mapping. Data mapping in general is an annoying problem, I think. And this problem needs to be solved. And if you're writing papers on processing in memory, if the reviewers are telling you that, oh, but you need to change the data mapping mechanism, just tell them, yes, you need to change the data mapping mechanism. Because as I said, existing data mapping mechanisms are developed with this as a center, right? As a result, existing data mapping mechanisms try to maximize the bandwidth into the main GPU, for example, or CPU. For example, they do cache block interleaving across memory channels. Cache block 0 is here, 1 is here, 2 is here, 3 is here. But if you're operating on cache blocks 0, 1, 2, 3 at the same time in memory, clearly you're not going to map your data that way, right? That would be actually stupid to map your data that way. So you need to change the data mapping mechanism. And the reason is that you're trying to enable some other feature than the current system. And you can quote me or review if you want, or respond to the review. Okay. And this paper actually tackles both of the problems from a GPU context and developed some mechanisms based on compiler and also empirical observations in terms of how the data is mapped in existing GPUs. But I will not go into the details of it. This is one example mechanism. And you can also read this paper if you're interested in GPUs. This tackles the issue of how to schedule code, actually, which is not easy. Okay, let's take a look at coherence. This is actually an old slide. We have much from the 4-page shorter paper called Lazy PIM. We have the newer version that has a much better version of this, I think. So basically, we wanted to examine the potential of breaking an application and partitioning it between the processor and memory. And the memory consists of 3D stack logic plus memory. And we looked at a bunch of applications over here, graph processing, clearly, in-memory databases, another example over here. And in-memory databases are actually very interesting because the trend in in-memory databases today is to cater for different types of execution. Did anybody hear about the HTAP workloads? It's called hybrid transactional analytical processing. And the idea over here is there's some part of memory, some part of the database where you do scanning of the database. Those are called analytical queries. Essentially, you query a lot of things to find out something about the database that you have. For example, if you're looking for I don't know, we looked at the bitmap indices earlier, right? If you're looking for the students who go to TU Wien and who are born in, I don't know, Switzerland, and who make this much money, that's essentially an analytical query where you actually query lots of parts of the database. It's it's another scan. It's essentially scanning operations. Essentially, you're really scanning across the database. And it turns out that's a streaming. You do a lot of streaming while you're doing that, and you don't do a lot of updates. You're basically doing a lot of reads. But there are also transactional parts of a database where what you're doing is really updating the database with a transaction. And those are much more targeted. You're not really scanning the entire database, but you're really updating, for example, a student's record or some record. And these have completely different characteristics. And it turns out it makes a lot of sense to execute the analytical parts of the database in memory because it's extremely memory intensive and you're not doing many updates actually. And they're relatively simple operations. As we've also seen with the ambit work, right? You execute a lot of those in memory. But the transactional parts, they have relatively good locality, and they need also a fast performance. So an out-of-order core that's in the CPU is a good place to execute. That's how we partition these workloads in this particular case. Transactional parts of a database are executed in the processor, analytical parts are executed in memory. Now, of course, while you're doing that, they may collide with each other, right? While this transactional part is updating some memory location, the analytical part may be reading that location. So you need to ensure that they don't conflict with each other. This is one example workload where you can get these conflicts a lot, depending on the rate of your transactions and updates and whatever your analytics is touching, especially if you have many, many clients that are executing the code on the database. And it turns out, essentially, if you use existing coherence mechanisms, sometimes you may not get a lot of performance, although in this case, non-cacheable works well. So basically, what we look at in this graph is if you partition your workload somehow between the CPU and the GPU, and my student Amirali did a lot of partitioning to be able to come up with a good partitioning, you get a lot of performance if there is no coherence overhead. Ideal PIM means that there is no coherence overhead, and the performance improvement is about 50%. You do simple functional floating here. And again, actually, our new paper has better results. These are relatively small data sets. We looked at bigger data sets. In bigger data sets, you get a lot more. It's more like 3x or 4x. I don't remember the number, actually. As your data sets become bigger, when you partition your workload between the CPU and GPU, the processing and memory benefits become much larger. Of course, this is ideal PIM. Ideal meaning that there is no coherence overhead. You partition your workload, and magically, you ignore all of the coherence overhead. If you use traditional coherence mechanisms, then the story is a bit different. Fine-grained coherence is very similar to the cache block-based coherence mechanisms that we have today, like the MESI protocol. Do you guys know about the MESI protocol? Some of you do. Okay, I don't want to go into it, but you can watch my coherence lecture or read this paper, but this paper really doesn't talk about that. I have a lecture on coherence and consistency that I really like because it explains things in a very simple way. You can take a look at it. But basically, the fine-grained coherence mechanism says whenever you're touching a cache block, first you need to get the permissions for that cache block. That's the idea. So whenever you need to read or write to a cache block, you need to get permissions. Unless you have exclusive permissions for that cache block, which you've acquired by some special mechanism in the coherence mechanism. If you have the exclusive permissions, then you can do anything to the cache block without telling anyone. But otherwise, you need to get the coherence. So if you do fine-grained coherence, you can see that you don't gain much benefit, right? Except for some cases. On average, you gain about, I don't know what that is, maybe 10% benefit from processing in memory. That doesn't sound very good, right? Your potential is 50% with no coherence overhead, but you're gaining 10%. Coarse-grained coherence means that essentially, this is called, there are multiple versions of it, but you're locking the entire region that you're operating on. It's not fine-grained. Whenever you're touching a cache block, you acquire permissions. If different parts of the code are touching different cache blocks, then fine-grained coherence is great, right? In coarse-grained coherence, you're locking the entire region that you're going to operate on, and nobody else can touch it while you're operating on it. And this turns out to be even worse, as you can see. That's an existing mechanism also. And non-cacheable, this means that basically, this is another approach to coherence, which means that you're not going to cache the parts that the PIM engine can operate on in the CPU. Basically, CPU doesn't do caching for those regions where it can potentially share data between the CPU and PIM. It turns out that's the worst approach in existing approach. So you actually lose performance, as you can see. So this shows the importance of caching. It works, in this case, really well, because you have these huge analytical queries that happen to be good, and transactional mechanisms don't lose a lot of performance, apparently. But this depends on the workload, of course. But basically, the takeaway is, if you look at traditional coherence mechanism and apply them out of the box between CPU and PIM, it leads to a lot of data movement across the chip, right? Because for the fine-grained coherence, for example, whenever PIM needs to touch a cache block, it needs to get permission from the CPU, because CPU has the coherence directory. That's the assumption. But if you put the coherence directory into PIM, the CPU needs to get permission from the coherence directory that's off-chip. So essentially, coherence communication leads to a lot of off-chip communication and actually leads to performance loss or the lack of benefits from PIM. So how do you actually bridge the gap, basically? How do you come up with a coherence mechanism that gets most of the benefits of ideal PIM with, of course, not a lot of complexity? And that's the idea in this lazy PIM paper. I'll give you the idea very quickly, but I'd recommend you can take a look at it. I think it's very interesting, but it's still a bit overhead. I think there's still need for mechanisms that have even less overhead. And the idea is actually very simple. Whenever you start executing some code on the memory side, the memory side records which cache blocks it has touched, reads and writes. And it basically records them in two separate signatures. You can think of these as Bloom filters, actually. These are Bloom filters, again. You record the addresses in Bloom filters. And at the end, so you have some code that says this is the beginning of processing in memory section, and this is the end of the processing in memory section. When the end of the processing in memory section is reached, these two signatures are sent to the CPU, and the CPU checks if it actually touched any of those cache blocks that were indicated, that were recorded in these signatures. So of course, CPU needs to also record a signature in this case. That's the idea. It sounds simple, but it's not actually easy to implement. That's why you should read the paper if you're interested. But it does lead to a lot of performance benefit, actually. This is, again, old results. We found much better results as we improved the mechanism. So you basically bridge the gap. You get most of the performance benefits of an ideal PIM with no coherence overhead with some additional complexity. Does that make sense? Yes, please.
Not completely, because what happens if there is a conflict?
Oh, yeah, I didn't tell you exactly what happens. Yeah, of course. So what happens if there's a conflict? If there's a conflict, so the PIM engine is a little bit more complicated. If there's a conflict, the PIM engine doesn't push its updates to memory. So there needs to be a buffer in the PIM engine to buffer the speculative updates that it's supposed to do. And those updates truly update memory only if there's no conflict. If there's a conflict, basically you blow away everything that you've done and you restart from the beginning. Does that make sense? So in a sense, this is actually very similar to transactional memory type of approaches. The key difference is, we didn't want to go into full transactional memory. The key difference is the CPU doesn't need to support any transactional memory. The CPU just needs to record these signatures, but CPU never rolls back, basically. CPU sends these PIM execution, we call it PIM functions, to memory. And if there's a conflict, memory rolls back, but CPU never rolls back. So you can keep the existing CPU for the most part. You just need to develop the new mechanisms in the memory. Does that answer your question? Of course, the goal is to minimize these conflicts. And that requires, that's a function of multiple things. First of all, how do you partition between CPU and PIM? And the second is, how big are your Bloom filters? If you have too small Bloom filters, you will get a lot of conflicts also, assuming you have the data conflicts to begin with. Okay. Okay, I'd recommend reading this if you're interested. And again, as I said, if you are interested in a short version, there's a short version. Longer, better version with a lot more data. That's the longer version. And I think this is actually not just about PIM. It's really more about this could be used for other accelerators also, in my opinion, although in the paper we didn't really evaluate it. So it could be used in a CPU-GPU context as well, potentially, but we didn't evaluate that in the CPU-GPU context. Okay. So clearly, we've talked about virtual memory. So I think this is actually a good solution. This is the only solution that I know of so far to coherence that actually tries to solve the coherence problem. Because if you remember, in Tesseract, we don't have a coherence problem because everything is essentially everything is message passing based. In PIM-enabled instructions, again, there is no coherence problem because we ensure that coherence problem doesn't exist. In function offloading that we've done in the past, there is a coherence problem, but the assumption is that we somehow solve it, but there's no solution. We just rely on existing mechanisms, but existing mechanisms may not be good, so you need to be extremely careful. So this is the only paper that I know of tries to solve the problem, but I think still the mechanisms are relatively complex. If you read the paper, you'll see what I mean. It has similar issues like transactional memory. Transactional memory is complex, and I think this is also complex. It's good to do, but maybe there are other mechanisms that are less complex. Okay. So virtual memory we talked about. Here I think we need more solutions also. And there are also other issues which I'm not going to go into, but once you have processing in memory, you should also look at data structure design for processing in memory, because maybe the way we design the data structures today is not the best way. Maybe you should have different types of data structures. And also maybe you should parallelize the data structures in processing in memory, because we know how to parallelize data structures across cores today very well. If you actually parallelize the data structures across your cores, but if you don't do that in memory, it might be much better to execute things in the cores, because you parallelized everything and there are many, many caches that the data structures are operating on. It's sometimes better to actually do that compared to moving the code to memory. And this paper actually looks at that trade-off. And it's an early paper. I think there is more work to be done in this area as well. Okay, and then simulation infrastructures. We're going to talk about Ramulator a little bit more, but we recently released the PIM version of Ramulator. Hopefully there will be better versions of it soon. And I think we're trying to extend this FPGA-based infrastructure for processing in memory benefits also. We'll see how that goes. And I think as I said, processing in memory is very general, right? We should really be doing processing across the memory hierarchy. I think SSDs are one other place to do this processing in memory. I think that's easier to do this in SSDs, but SSDs are very complicated, so it's really important to understand how to do this in SSDs, I think. And I think this is another simulation infrastructure that we've developed for SSDs, if you're interested in this. There's no processing in memory support here at all at this point, but I believe somebody will develop it. If you're interested in developing, let me know.
So this would be interesting to, for example, search for files or search a database.
Exactly. If your data doesn't fit in memory, clearly SSD has much bigger. And if your memory doesn't really have the files necessarily, right? It's much better to search for a lot of files over there, yes. Whenever your data doesn't fit in memory, I think this is a good place. Or if you're doing search on persistent data and your memory is not persistent. Okay, so I think I'll talk about new application use cases a little bit also, very quickly. This is going back to the bioinformatics, if you remember. I think this is another application. So I think people need to look at more and more applications of processing in memory. I'll talk about this very briefly, very quickly, just to whet your appetite. But we've been looking at a lot of applications, actually, and I'm giving you a lot of examples. This is one we'll get back to. Clearly, this one we wanted to examine also, because we've been examining a lot of other more larger workloads, but that's why we wanted to examine the smaller workloads also. And we saw a lot of data movement bottlenecks, as you remember. Let me give you the basic ideas over here. I'm not going to go through this in detail because truly understanding this really requires some more time. But if you're really interested, you can read the paper. But basically, as I motivated, genome read mapping is a key problem. That's the beginning of many types of genomic analysis, and it could lead to a lot of benefits, I think. And it's really an approximate string matching problem, as we've discussed. Basically, you want to find the best fit of some number of character strings in a bigger string. But alignment is very expensive. So basically, we wanted to develop an in-memory processing algorithm in this case to accelerate mean mapping by reducing the number of required alignments. So if you remember my first lecture, I said that we want to have a filter that quickly tells us whether this particular fragment is going to match this location in the reference. Here, we wanted to accelerate that filter. And it turns out, if you use in-memory processing with 3D stacked memory, you get significant speedups. Again, I think this is low. We didn't optimize it. It could be much higher if we optimize the obvious things that we think could be useful to optimize. But let me give you an idea over here. Basically, the key is coming up with a new representation of the reference genome in this case. If you want to process things fast inside memory, we essentially represent the reference genome using bit vectors for different bins of reference genome. And basically, we encode some information. And the information says basically, for this bin 0 is part of the reference genome, does the string AAAA exist in that bin? So it's a bit vector, the pre-processed reference genome, that tells whether that particular string exists in the bin. So for each bit in this bit vector, you have an associated string. And whether or not the bit is 0 or 1 tells whether that particular small string exists in that large bin associated with the reference genome. So you encode your reference genome this way. And your reference genome has many bins, of course, because it's huge. And you basically lay out these bit vectors in a bank this way. Now you can do the processing very quickly. Basically, let's assume that you have a small fragment that you got from the chopper, from the machine. And that is all A's. What do? Basically, using all A's, you activate this row. So all A's map to row 1 in this case. You activate this row. Now you have all the bits in bins 0 through t minus 1. And you basically check whether there is a 1 in that, whether any of these bits is 1. Now, what does that indicate? Let's assume that none of them has a 1. If none of them has a 1, that means that none of them contain this particular substring, and you can move on. You don't need to do alignment in that case. Right? Of course, there's an algorithmic part of this also that I didn't describe to you. But that's the idea over here. If you have some 1 over here, then you basically have an accumulator that basically counts, saying how many of these things that I index these bit vectors with actually had a 1 in this particular bin. And you basically count how many of them. And at some point, you say, OK, I've seen enough 1s for this query that I'm doing in this particular bit vector. If there are enough 1s, that means that you want to do alignment for that particular region of the reference genome for the particular fragment that you're looking at. Now, I said this very quickly. I don't want to go into a lot of detail. But if you're interested in the algorithm, you should really look at the paper. So my takeaway is, if you really want to take advantage of processing in memory, first of all, you really need to design your algorithm to make it work with the structures you have. And you really need to map your data in an appropriate way so that you can do these queries in parallel. So in this case, we actually laid out the bit vectors, as you can see, column-wise, so that we can check a lot of bins at the same time. When you get a fragment, you can check t bins, essentially, at the same time, where t is the size of your row. And it could be 8 kilobytes, let's say. If it's 8 kilobytes, that's a lot of bins, right, that you're checking at the same time. OK. I already said this. The layout of bit vectors in a bank enables filtering many bins in parallel. And there's customized logic for accumulation and comparison per the genome segment. And that's very, very simple logic, actually. Actually, if you extend mbit a little bit, it requires more operations inside DRAM. This algorithm is a very good fit for mbit also. But we didn't do that in this case. We used the 3D stack logic layer in this case. OK, and you get a lot of performance, actually. These are across real data sets. These are real genomes and real read sets. And you get significant performance improvement. And because we changed the algorithm, we actually get a better filter as well. Because it's a completely different filtering algorithm than the past. Since you don't know the earlier filtering algorithm, since we didn't discuss that, it makes no sense to discuss the false positives and why it's reducing, but you can read the paper if you're really interested. And there's more work to be done in this area, certainly in genome analysis. But it's an algorithm architecture co-design approach. Okay, so let me see. I think I don't need to talk about more. But essentially, it's another interesting property. This is actually a universal filter that can be applied to any read mapper. We applied it to one mapper over here, but it could be applied to any. And this is the paper that talks about it. Okay. So if there are more open problems, and this is the paper that you're reading, I don't want to talk more about that, but I think we covered the big ones. Any questions? We're getting to the end of the processing in memory lecture. We'll switch to some other topic. How much time do we have today? I mean, not a lot of time. I was hoping we would start latency today, but we'll see. Okay, let me go over some of these philosophical parts quickly then. So I think this is a new paradigm. Clearly, there will be a lot of resistance to a new paradigm, and that's true. But that's not new. So I think computer architecture today is actually changing a lot, and this is actually a good time to be thinking about these big ideas and new paradigms. Maybe there's some other paradigm that we haven't thought of also. If you think about it, I'd be happy to know. Essentially, at this time, we can really revolutionize how the computers are built, in my opinion. And I believe we need to, and we can invent new paradigms for computation, communication, and storage. But of course, there will be a lot of resistance to it also. But this is not new. Has anybody read this book? Has anybody heard of this book? You read it?
No, I heard that.
You heard about it? It's what?
I read an introduction of this book.
Okay, yeah, then you should read the whole thing. It's not an easy read, but but this is a book that's about the philosophy of science. It had a lot of impact, actually, on philosophy of science. It had a lot of critiques also. But essentially, Thomas Kuhn in this book analyzed and also hypothesized that science goes through these 3 cycles, and in the end, revolutions are enabled. Normal part of science is you have some dominant theory that explains things as business as usual, and exceptions are usually considered anomalies. I think of this as like computer architecture in the 1990s, for example, or maybe even 1980s. Essentially, you had a paradigm, and that was very strong. And the paradigm was you have a single processor, right? Single processor is superscalar, out of order, and that's how you get performance. You keep improving all of the structures associated with that processor, and that's how you get performance. And people write single-threaded code, and magically they become faster, right? Magic is, of course, how you design the engine. But there's a dominant theory, and everything else, okay, you don't get good performance on this thing, or you don't get good performance on this thing. They're anomalies, right? You basically dismiss them. And actually, he has a very good way of explaining how these things happen in real science. Dismissing them partly, for example, happens through the review process. People say, okay, I don't buy this, and reject. That's another way of dismissing these things that are like outside the normal science, if you will. But at some point, you have so many exceptions that you go into, I should have ordered these differently. At some point, you have so many exceptions that people start questioning, okay, maybe this is not the right thing to do, right? And then you go into more pre-paradigm science. There's no clear consensus in the field, and things shake up a little bit. And I think computer architecture is kind of like that today, because clearly we know that a single processor is not good, but we don't know what's really good. We know some basic principles that may be good, like heterogeneity is good, but again, we don't really know how to do things. And we know that data movement is a bottleneck, but we don't really know how to solve it. So basically, there's no clear consensus in the field. And at some point, revolutionary science happens, and you re-examine all of the underlying assumptions, and some scientific revolution emerges. I think of computer architecture at this point like this. Computer architecture is clearly not a science, right? It's more of an art plus engineering at the same time. It's engineering plus art, however you would like to put them together. You cannot remove the art component out of it, unfortunately, but it's there. But I think the theory applies over here also. Basically, we need to examine the underlying assumptions and come up with a new normal science somehow, assuming you follow this theory. Right? And if you're interested, that's him, and that's the book. I like this book. I used to give this book, actually, for people who win the programming assignments in my lectures. I don't know if they read them, but They could at least sell it for $5 or something like that. Or you could get the Kindle version, which I don't know if you can sell the Kindle version. Okay, let me conclude with a little bit more philosophy. But I think this philosophy is also important because it points out to something bigger than we've been discussing before. So this is Maslow's hierarchy of needs. You could argue that all you need is speed and nothing else, right? If you're speedy enough, you'll fix all the security and reliability and energy problems. Of course, energy may not be harder. Basically, we want high performance, we want energy efficiency, and we want low latency in computing architecture. And I put data-centric underneath all of that because I think this data-centric architecture then it gives you high performance, energy efficiency, and low latency at the same time. And the key is really minimizing data movement, and I really believe that. So let me conclude. This is going to be, again, a little bit more motivational. But some very famous architects said architecture should be based upon principle and not upon precedent. Precedent means what comes before, right? And principle is clearly principle, right? Does anybody know who said this? It's a real architect, not a microarchitect. He designed buildings, basically. So if I show you this picture, does anybody know who that is? Probably not in the middle of Europe. Although he's very famous. He's actually taught in European architecture classes also. This is a very famous American architect. He's called Frank Lloyd Wright. Does that name ring a bell? I guess so, yeah. And he didn't design this because this would be a precedent-based design, meaning that this is what comes before, which is not bad, right? It's functional. Maybe I don't mind living here, but it's like where everybody else lives. And it's cheap, probably. But he instead designed this. You may have seen this one. This is Falling Water, his masterpiece. One of his masterpieces, but it's considered his real masterpiece. And this is based on some principle. Basically, if you look at, it's really based on a waterfall. It's in a beautiful environment. This is actually very close to where I used to teach, Carnegie Mellon University. It's about 1 hour, 15 minutes drive from there. If you drive fast, you could get faster, of course. But I used to give this as an assignment to the students. Go there and exercise your creativity, basically, and understand the principles. But essentially, these cantilevers are modeled based on the shape of the waterfall over here. And there are a bunch of other interesting things inside here. So there is a principle over here, which I will not go into. If you're like Wikipedia, this is one version of the principle from the Wikipedia, basically. It's organic architecture. It promotes harmony between human habitation and the natural world through design approaches, so sympathetic and well integrated with its site that buildings, furnishing, and surroundings become part of a unified, interrelated composition. It's nice. And he actually showed a lot of the examples of this principle, even though he never wrote well about it. He didn't write, he really built. Okay, so that's another. Let's look at another example. Maybe you're more familiar with this sort of structure. This is a train station. It's a precedent-based design again. A lot of them exist. They all look like this, I think, or something similar. But this is another design. This looks a bit different, right? I mean, some of it is similar clearly, but there's some principle to this design. The first time I went here, I was amazed, actually. This picture doesn't do justice to it. Has anyone been here? No? Maybe something similar exists here, but I don't know. Okay, that's one design. There's another design that has similarity. Has anyone been there? That's in Lisbon. I don't know if I had a side channel here. Oh, I don't have a side channel. That's great. Although there is a side channel here. And maybe some side channels here that I cannot read. This is in Zurich. Span of Stadelhofen in Zurich. This is in Lisbon. Gare d'Oriente. And it's based on some principle. This is the blueprints of that principle. This is in, does anybody know where that is? If you travel, is it?
Valencia?
Valencia, that's right, yes. Yes, it's in the City of Arts and Sciences in Valencia. And you know the architect? Okay, not yet. You will know soon. So these are all from the same architect. They're all principal. How about this one? If you've ever been to New York, you should know this one. This is called the Oculus. It's very similar, actually, if you look at the principles. Well, it's principle-based design. This was designed by Santiago Calatrava. He's the architect. He was an ETH alumnus also, actually. He did his PhD in civil engineering. And he charges people a lot for these principle designs. That's good for him. But my point here is this is clearly a principled design. It's actually very costly. According to Wikipedia, this is about $4 billion. It cost New Yorkers. And there were a lot of complaints about this. Actually, if you go back to the falling water that I showed you, the Kaufman family ordered it, and they basically had to stop Frank Lloyd Wright. They said, we're not going to pay you any money. We're done. Because it was also expensive. So clearly, this is also expensive. But it's a new principle-based design. You don't have the regular transit. There's actually a train station also. Underneath, there's a huge metro station over here that connects you to the train station as well. Essentially, you pay the cost of a new technology. That's the way I look at this. This is a new technology that's much better than the old technology. It's a more principled design. Well, to get there, you need to pay some cost. It's not easy. But once you get there, there were a lot of complaints before. Now, New Yorkers who complain, now they go inside there and enjoy it because it's so beautiful inside. So once you pay the cost to shift to a new paradigm, maybe you'll enjoy it. That's my point over here. Okay, basically this is the principle that he uses. It's a more zoomorphic architecture. And clearly this looks like a bird, right? Although critics, I think, wrote articles saying that this looks more like a dinosaur than a bird without a beak, without basically parts of the dinosaur is missing. Okay, anyway, so I think the question is, do we have an overarching principle for computing? I don't know, and I put this over here because some people think that this is one of the best computers in the world. I don't agree, actually. I think this is one particular design of a computer, perhaps, but maybe it's not the best because it's not best at everything, right? Clearly, I cannot compute as fast as some of these machines, but I can do some things much better than the machines. But this has some principles, I think, that we may or may not fully know. But do we know the principles of computing that we base things on? I think processor-centric principle is probably not a good principle. It may be one of the principles, but it's clearly the only principle that we've been following for such a long time. And maybe it's time to change that. And this is actually I think, implications on psychology and biology also. So I mentioned that I have a degree in psychology also. And at the time I was studying psychology, the paradigm of psychology was, oh, we would like to understand humans based on how computers work. That was actually a paradigm when the computing revolution happened in the 1950s, 60s, 70s, 80s, 90s. That paradigm increased, and people said, okay, we should use computing as a paradigm for understanding humans. And I think that failed miserably, in my opinion, because computers were not built with the same principles that we have humans with. Maybe we should somehow take a step back and think about the principles with which we build the computers going forward. And that may enable us to understand this better also. That's what people are doing with neuromorphic computing today. Again, it's limited. Maybe it's not perfect, but it's good to look at these different approaches where we look at more biological basis for building computers. Anyway, there's a lot more philosophy to do here, but I'm not going to do that. Essentially, I'll conclude this particular part of the lecture. I think it's time to design more principled system architectures, not just computing architecture, not just part of the architecture, but system architectures in general, or computing architectures, to solve the memory problem. We have a huge memory bottleneck, and everybody recognizes it, but we're still doing business as usual, in industry at least. So we need to design complete systems to be more balanced. I started this lecture saying that we have a huge imbalance, right? High performance and energy efficient. And I think all of this requires to be data-centric or memory-centric, which means that we need to enable computation capability inside and close to memory and across all parts of the system where we are not doing it today. And I think this can lead to orders of magnitude improvements, and I've given you many examples of this. Right? Ambit, for example, gave you 60, 70x. The graph processing accelerator gave you 13x or so. I think there could be a lot more, actually. And other people are showing with new emerging memory technology, you can get similar improvements, maybe sometimes more improvements. Of course, that remains to be seen because those technologies are still emerging, right? And I think this can also enable new applications and computing platforms. And I will argue that if you're really extremely data bound, you need to do something different to enable these new computing platforms because we don't know what we're missing at this point. And I believe this could enable better understanding of the future also, or nature also, because I think, as I gave you that anecdote from psychology that failed, but maybe something else will not fail. And who knows what else it could enable. So I believe the future is bright, regardless of the challenge. And there are many challenges we've discussed in underlying technology and overlying problems and requirements. We can enable new things, but I think we need to think across the stack and design enabling systems. We should be cognizant of the fact that this is not easy. And this is going to be costly. So I think any new technology is costly. It's going to be costly here also. The key is enabling that transition to that costly environment. So we need to visit that, but we can get there step by step, as I mentioned. So I'll finish with an example. Maybe I'll ask a question first related to this example. Maybe I won't get the answer I'm looking for, though. Let me ask it. So basically, what do you think is the most important electronics technology in our lives currently? Maybe that's too broad. What has enabled a lot of what we use today? Okay, I'm not asking for a device. I'm asking for an underlying technology that has enabled many, many devices. Processor is one example, right? On the memory side, let me give you more hint. What has enabled this one? Okay, good. So I got the answer when I showed this one, I guess. I would argue that what has enabled this one is also flash memory, at least going into the future. But yeah, flash memory, I would say. So this was a very doubtful emerging technology for decades and decades, actually, for at least 2 decades, flash memory. It was developed in early 1980s, actually earlier than that also, and nobody really realized its potential. And actually, I have friends who were researching garbage collection of flash memories in late 1980s, early 1990s, mid-1990s, and basically they were getting comments from their viewers saying, they were writing proposals to the US National Science Foundation saying, I want to investigate garbage collection for this important technology. And they were getting comments saying, who cares about this technology? It's useless, it's nowhere. Right? That's the backward-looking mindset. But clearly, we've spent a lot of effort to enable this technology, and that has changed a lot of things we do in our lives. Right? I mean, I don't think this would exist without flash memory. Otherwise, nobody would store their pictures anywhere, right? You cannot put enough DRAM on here. And as a result, now we have papers like this, right? We know this technology really well, and we've enabled it, and we will continue to enable it, I think. So this is one example, and I think we need to enable processing in memory also. But this has come at a cost. I mean, it was a lot of infrastructure that was built from scratch to actually enable a technology like this. And if you go back 50 years ago, it was DRAM. You needed a lot of infrastructure to enable DRAM. You need a lot of infrastructure to enable flash memory. Now multiple memory is also like that, and I think we need that for processing in memory also. And that's why people are writing papers like this, and hopefully you're reading them. Okay, any questions? I think I went through the philosophy a little bit fast, but hopefully I hit the key points. So if there are no questions, let's go into a shorter part of the lecture.